We're now going to compute at least probabilities. The probability that a randomly selected female age 60 years old will survive the year is 99.186%, according to the National Vital Statistics Report. What is the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? So here we want probability at least one dies. Now let's think about this. To compute this probability, that would mean the probability one dies or two dies or three dies all the way up to all 500 die. Now, it is the case that each of those possibilities are disjoint, because you can't have one die and two die at the same time. And because they're disjoint, I could compute this, the probability one dies plus the probability two dies plus the probability three dies plus, all the way to 500 dying. Right? But that would be a heck of a lot of computation, most of which we don't know how to do. The only possibility we didn't cover here is what? Nobody dies. Putting a better light on it. The only possibility we didn't cover is all 500 survive. So the complement of at least one dying is all 500 survive. So rather than compute this by figuring all these probabilities out, I could do 1 minus the probability 0 die, which is 1 minus the probability all survive. Now that would be computed saying that's the probability the first survives and the second survives and all the way down to the 500th survives. And whenever you see and, you think multiply, multiplication. And in order to use the multiplication rule, we need to verify that these events are in fact independent. Is it reasonable to presume that these events are independent? In other words, does the survival of one of the women have anything to do with the survival of the others? No, it does not. How do we know this? Because they're randomly selected. They're not linked in any way. So this would be the probability first survives times the probability second survives times the probability the 500th survives. Right? Or it's 0.99186 times 0.99186 times 0.99186 500 times, which is 0.99186 to the 500th power. And what do I get if I do this computation?
0.017.
0.017? Mm-hmm. Anyone want to second that motion? 1 minus this is 0.9832. Okay.
187. Got it.
Let's do 0.983.
I messed up my decimal.
983. So if we randomly selected 100 different groups of 500 females that are 60 years old, about 98 of the times we're going to find at least one of them dies during the course of the year. So out of a group of 500 randomly selected 60-year-old females, is it unusual for at least one of them not to survive the year? No. In fact, quite the opposite is the case. If we were to randomly select 560-year-old females, it would be unusual if they all survived. There's a 98.3% probability at least one of them will die. This has been a rather morbid class, hasn't it?